All right, today we are going to dive into a concept that starts off super simple, but trust me, it ends up twisting our whole idea of what it means for two things to be close. It's one of the weirdest and most fascinating ideas in all of data science. Let's get into it.
So it all kicks off with a question I know you've asked yourself probably 100 times while endlessly scrolling. How in the world does Netflix know exactly what I want to watch next? Is it reading my mind? Is it magic? Well, the real answer, it's a lot more interesting than magic.
You see, Netflix's recommendation engine is all about data. Yeah, of course, it looks at what you've watched, how you've rated stuff, all that. But the real secret sauce, the magic ingredient, is finding other people just like you and seeing what they're watching. The whole mission is to find your data twin.
Okay, so how does a machine actually find your data twin? This whole idea of finding people like you is powered by a machine learning algorithm that is, believe it or not, wonderfully simple and intuitive.
It's called K-nearest neighbors, or KNN for short. And the logic is really straightforward. To make a guess about something new, you just find the K most similar things that already exist, your nearest neighbors, and then you basically take a vote. So if you want to know if you'll like a new movie, KNN finds, the 10 people whose tastes are most like yours and just sees what they thought. Majority rules. Simple. But that brings up a pretty huge question, doesn't it? When we're talking about abstract data points and not, people on a map, how does an algorithm actually measure closeness? What does distance even mean?
Well, it turns out there are a couple of classic ways to do this. And to get it, we don't need any complicated math. We just need to think about two different ways of getting from point A to point B.
So the two most common ways are called Euclidean distance and Manhattan distance. Euclidean is probably what you remember from school. It's the direct, straight-line path. Just think as the crow flies. Manhattan distance is different. It measures distance by only moving along a grid, like you're walking city blocks in Manhattan. You can only go up, down, left, or right. No cutting through buildings.
And here's the perfect way to picture it in your head. Euclidean distance? That's the bird, flying in a perfectly straight line. Manhattan distance? That's the taxicab, stuck on the ground, having to follow the strict grid of the city streets. Two totally different paths and two totally different measurements of distance.
So there we have it. Problem solved. We just pick one of these distance metrics, find our nearest data neighbors, and we're good to go. We can build recommendation engines all day. It's that simple, right?
Yeah, not so fast. This whole thing works beautifully when we're comparing just a couple of things, like your ratings for two different movies. But what happens when we're comparing you based on hundreds of movies, or thousands? When you start adding more and more data points, more dimensions, things get really, really weird. And this is where we run smack into a huge wall. It's a famous problem in data science, and it has this wonderfully dramatic name, the curse of dimensionality. One of the sources for this explainer uses a quote to capture what it feels like to work with this kind of data, and it's just too good not to share. In high-dimensional space, nobody can hear you scream. It's just a lonely, strange place to be. So what is this curse, really? The term itself was coined by a mathematician named Richard Bellman, and it basically refers to this whole collection of bizarre, counterintuitive problems that just pop up when you start working with data that has a ton of features, or what we call dimensions. To get your head around just how strange this gets, let's start with a really simple example. In 2 dimensions, a circle fits nicely inside a square. Go up to 3 dimensions, a sphere sits pretty snugly inside a cube. In our normal, everyday world, that sphere takes up a pretty good chunk of the cube's space. Okay, but now watch what happens as we add more dimensions. In 2D, the circle is about 78% of the square's area. In 3D, the sphere is about 52% of the cube's volume. But get this, by the time we hit just 6 dimensions, that sphere's volume just plummets to only 8% of the cube's. And as you keep adding dimensions, that ratio just gets smaller and smaller, heading straight towards 0. So where did all the volume go? It's like it all gets sucked out of the middle and rushes to the far-flung corners of this high-dimensional cube. The center of the space, where our sphere is, becomes effectively empty. The space itself becomes vast and kind of lonely.
And this weird, empty, lonely space, it has a truly shocking consequence. It leads to a revelation that just completely shatters the entire foundation of our k-nearest neighbors algorithm.
This all leads to this bizarre phenomenon called distance concentration. Because everything is shoved out into the corners of that huge empty space, the distance between any two random points starts to look almost exactly the same.
everything becomes equally far away from everything else.
I mean, just look at this. On the left, in only 2 dimensions, you see a nice, healthy spread. Some points are close, some are far, it all makes sense. But by the time you get to 1,000 dimensions, over on the right, look at that. All the distances have just collapsed into a single, tight spike. The difference between near and far has literally vanished.
The practical consequences of this are, well, they're devastating for our algorithm. The data becomes so spread out it's basically sparse, like a few grains of sand in a desert. And here's the killer. There's no longer any meaningful difference between the nearest neighbor and the farthest neighbor. The very concept of nearness just loses all meaning.
So the bottom line is this. The entire idea of a neighborhood, of finding a data twin, the very thing that powered our whole Netflix recommender, it just completely breaks down.
And look, this isn't just some quirky math problem. This is a fundamental challenge in modern AI and data science. It affects everything, from the movies you get recommended, to how scientists analyze genetic data for medical research, all the way to how financial systems try to model risk.
Which leaves us with one final, fascinating, and kind of mind-bending question to chew on. If our basic intuitive understanding of distance turns out to be an illusion when data gets really complex, then what does it truly mean for any 2 things to be similar at all? That's a question data scientists are still wrestling with every single day.